Welcome back to SN Tutors. So, last time we talked about SN2 reactions. This time we're going to be talking about SN1 reactions. So this is a two-step process. I know it can be confusing because there's a 1 here and it's 2 steps, and for SN2 it's 1 step, but just remember that. So the 1 refers to unimolecular substitution. So this happens when the leaving group, so we'll just redraw what we had last time. So this happens when the leaving group leaves before the nucleophile comes in. And this can happen for a number of reasons. The most common reason is that the nucleophile isn't reactive enough to attack right away. So let's put our leaving group right here and we'll make this an H or something. So the leaving group just leaves right away. Then what we get here is a secondary carbocation, which is highly unstable. But what happens now is when the nucleophile comes in, it could come in from the top or from the bottom. So this gives you a mixture of stereoisomers. You could have this, or you could have this, right? And it's a 50-50 mixture. We call this a racemic mixture, right? Okay, so that pretty much sums it up, but I'll leave you guys with just a couple things. Number 1 is that the nucleophile that happens in SN1 reactions is usually, or the nucleophile that attacks rather, that is usually neutral, because negatively charged nucleophiles are strong enough to do SN2. And then 2, since we're generating this carbocation, the electrophile, which is the tetrahedral carbon initially, is usually, I'll just refer to it as this, La+, is usually secondary or tertiary, because a primary carbocation is extremely unstable, and it's very, very unlikely that it will go through an SN1 process, right? And then there's also one more thing that could happen. So let's say we had an oxygen here. Instead of a hydrogen. So a hydroxyl group or something like that. When this leaving group leaves, this has electrons, lone pairs that are delocalizable, and can actually go down and stabilize this right here. So what this will look like is a much more stable version of a carbocation, because a carbocation, in the instance that I just erased, was open shell. However, the new carbocation, if you use what this is called cystidionization here. So if you use a cystidionization, then your sp2 hybridized intermediate looks like this, where the oxygen has the positive charge. You might think to yourself, Well, oxygen carrying a partial charge is very unstable, right? And it is. But it's a lot more stable than an oxygen being neutral and having an open shell atom. In this case, it would be the carbon. But now when the nucleophile attacks, it would be like this, and then you would just have to draw in your OH. Right. So that pretty much sums up SN1. I hope this video was helpful. Please subscribe to the channel if you liked it, and I'll see you next time.